Lesson 1.2, Part 2 is where we're set to go today. Where we were supposed to go yesterday, but we're going today. So we have 4 topics here to continue on. We are looking at continuity, increasing, decreasing, boundedness, and extrema. So when we get to extrema, we will be learning something new on the calculator. So you'll have to have that at that point. So first of all, continuity. A function is continuous. Okay? Official definition, if there are no holes, breaks, or asymptotes. In order for a function to be continuous, we must check for holes and asymptotes. So, continuity. You put your pencil down, you can draw the whole graph on the paper without ever lifting it up. Okay, that's, basic definition of continuity. Officially, holes and asymptotes are what could cause a graph to be discontinuous. Now, whether right here where it talks about checking for holes and asymptotes, I talked a little bit about this yesterday when we were talking about domain, but we have to start and take the denominator equal to 0. Okay, those are, anytime you have the denominator equal to 0, the result of putting the denominator equal to 0 is going to result in either a hole or an asymptote. Okay, so we'll start by putting the denominator equal to 0, but then the other part of this is that we can also investigate graphically. So kind of like with domain and range, or at least domain, where we're going to look at the algebra, and the algebra here is important because you don't always get the graph option, but then we'll also go and look at the graph. Bless you. So, first one here, an example of a hole. Well, before you do anything with these, you always want to look, let's start with denominator equal to 0. Okay, so holes and asymptotes, denominator equal to 0. Well, what do we know here? If you set your denominator equal to 0, x plus 2 equals 0, and what do you get? Subtract the 2 over, and x equals negative 2, yes? So here's what I know right now without doing any work on the equation. Because putting the denominator equal to 0, I got x equals negative 2. I know there's either a hole or a vertical asymptote at that point. Okay? Now, the question is, which is it? And what you need to do to decide which is there any factoring that can be done in that equation right there? So x squared minus 4 over x plus 2. X plus 2 doesn't do anything. But do you remember how to factor x squared minus 4?
X minus 2 and x plus 2.
Does that sound familiar? I call it difference of squares officially. But when it's 2 perfect squares being subtracted, it can factor into 2 parentheses. X squared breaks into x and x. The square root of 4 is 2, so 2 and 2. Multiplying to be a minus is a plus and a minus. My denominator is x plus 2. What do you notice about the numerator and the denominator? They both have a factor of x plus 2 that can cancel. So my denominator cancels. Because my denominator is able to cancel, I know that there is a hole at x equals negative 2. And that's because that x plus 2 factor canceled. So if you set your denominator equal to 0, but that denominator is able to be canceled out, it's going to result in a hole. Now, vocabulary-wise, f of x has a removable discontinuity. A removable discontinuity is the fancy way or official way of saying hole at x equals negative 2. Okay? So a removable discontinuity is a hole. And when we talk about hole, it's basically the graph looks continuous, but there's like one little hole where it's not filled in. You won't even always be able to see that on your calculator unless you graph it in close enough. Okay? So that's one example of discontinuity, is there could be a hole. The other example of a discontinuity is there could be a asymptote. And specifically here when we're talking about an example of an asymptote, this is specifically a vertical asymptote that we're talking about here. Again, its denominator equal to 0. If I set my denominator equal to 0, x minus 3 equals 0. Add the 3 over, x equals 3. Now, and I guess technically it's where the denominator equals 0. So it's the same thing we talked about yesterday, that x cannot equal 3 and x cannot equal negative 2. Okay? With that in mind, what about that numerator? Is there any factoring that could be done? X plus 6, does that factor? No. No GCFs, no difference of squares. There's nothing that can cancel here. So because there's nothing that can cancel, okay, because there's nothing that can cancel, there is a vertical asymptote at x equals 3. Okay, so vertical asymptote. Official language. A vertical asymptote is a non-removable discontinuity. So a hole is a removable discontinuity. Vertical asymptote is a non-removable discontinuity. Okay? Those are the two types of discontinuities you need to be familiar with. Removable and non-removable, or holes and vertical asymptotes. Okay. Example 2. Determine where the function has a discontinuity and state whether it is removable or non-removable. So where is there some type of discontinuity?
X plus 3 equals 0.
Okay, so it's based on looking at the denominator. If we set x plus 3 equal to 0, then we're going to find, when you solve that, x equals negative 3, which technically that's where the denominator equals 0, so what do we know? X cannot equal negative 3. There is some type of discontinuity there. Now, the question is it removable in a hole, or is it non-removable and an asymptote?
Well, you can do like 3 parentheses, do x plus 3, x plus 3, x plus 3.
Not exactly. That'd be a lot easier. Okay. That numerator does factor. We learned it last year in Algebra 2 at one point. When? I don't remember. But it's factoring. It's factoring factoring the sum of cubes, because x cubed is a perfect cube. 27. Can we take the cube root of 27? We can. What's the cube root of 27? 3. 3 times 3 is 9, times 3 is 27, right? So it is a perfect cube. So this is factorable. Now, let me write it out right here so you have this form, because we'll talk about it on and off this year. This is factoring a cubed plus b cubed, is this form here. And it factors into a plus b times a squared minus ab plus b squared. Now I'm going to walk you through that, obviously, but that's the formula. So first of all, what is the cube root of x cubed? Cube root of x cubed is x, yes? What's the cube root of 27? 3. So every place there's an a, I'm going to use x. Every place there's a b, I'm going to use 3. So first parenthesis, when I factor this, is a plus b, or basically it's the cube roots and then just added. So in this case, it's going to be x plus 3. The trinomial is the one that's harder to remember. The first and last are just these cube roots squared. So x was the first one. X, when you square that, is x squared. The middle term is always the opposite sign of the first term, or the first parentheses, with the pieces multiplied together. So opposite of plus is minus, and 3 times x is 3x. The last term is always plus, and it's this second term squared, so 3 squared is 9. All over my original denominator of x plus 3. Well, what just so happens here? X plus 3's cancel. So, where does the function have a discontinuity? That's at negative 3. Is it removable or non-removable? Okay, because this canceled and we determined it to be a whole, okay, we have a removable discontinuity at x equals negative 3. So removable discontinuity at x equals negative 3. Fancy speak for saying there's a hole. And again, you can't rely on the calculator for that. Because if you graph it on the calculator, there's a decent chance that it's not going to show up at all.
So what do you graph, just the original thing?
The original, yes. And this is why I'm not encouraging you guys to just rely on the calculator, because if there's a vertical asymptote, yeah, that'll be obvious. Okay. And what do we say? Negative 3, so this isn't a good one to look at because it's way up high. I'm going to change my window real quick. I'm going to go 0 to 30. Oh, that's the wrong window. Dang it. Negative 10 to 10 was good for the x's. I want my y min to be 0, my y max to be 30, and see what happens. Okay. That looks like a regular graph there, doesn't it? Supposedly there's a hole at negative 3. Can we see it? No, we can't see it. If I trace over to negative 3, there's a hole in this area. But I can't see it. Okay? If I zoom in that area, you're probably still not going to be able to see it. Okay? I can't see anything. Now, if I type in the value, notice at negative 3, it says it doesn't exist. But I still can't physically see it. And so that's where you can't rely on the calculator for holes. Okay? Okay, questions there? Okay, let's look at B then real quick. Where does this function have a discontinuity in B? Where is there going to be either a hole or a vertical asymptote? Yeah. So x minus 2 equals 0. We solve that, and we're going to know that x cannot equal 2. There's some kind of discontinuity at x equals 2. Now, is it a hole or is it a vertical asymptote? Well, let's go back and see. X minus 2 in the denominator is x minus 2. Does my numerator factor?
Yes.
Okay, so let's factor it. X squared is x and x. I need numbers that multiply to be 2 and add to be 3. 2 and 1. What are my signs? Plus, plus. Do I have anything that cancels? No. If I don't have anything that cancels, that means that this denominator represents a vertical asymptote instead. Okay, so I know now that this is an asymptote, a vertical asymptote. Now, official language. Official language, what kind of discontinuity is this? Non-removable. Vertical asymptotes are non-removable. So we have a non-removable discontinuity at x equals 2. Non-removable discontinuity at x equals 2. Okay. Okay. Discontinuities. Set your denominator equals 0. That tells you the location. Figure out whether or not the factor cancels. That will tell you whether or not it is removable in a hole or non-removable in an asymptote. Okay. Now, when I say it's more obvious, what was this one? X squared plus 3x plus 2 over x minus 2. I'm going to zoom 6 to reset my screen. Okay, the other piece must be up high. Yeah, there's the other piece way up high. Can you see the vertical asymptote? Or you can't physically see it, but can you see the area where the vertical asymptote is? Okay, you've got the two pieces of the graph there, so you can tell. Yeah, it makes sense. Okay, that's one of our properties that we're talking about today, is discontinuity. Okay, questions there? Okay, let's talk increasing and decreasing. You did this in Algebra 2, Chapter 1 last year, because my Algebra 2 this year kids have already tested on increasing and decreasing. A function is considered increasing, or if a function is considered increasing, the x value increases and so does the y value. So x value increases just saying as you move right across the equation, so does the y. So as x increases, y increases, my graph is increasing. Decreasing. Well, decreasing as x increases, so as you move right across the graph, y is decreasing, meaning my graph is going down. And then we don't talk about this one a lot. The function is considered constant if as the x value increases, so as you move right across the graph, the y value stays constant. We talk about constant, we're talking about our horizontal pieces. Okay? Now, for each function, tell the intervals on which it is increasing or decreasing. I guess you're going to want your calculator right now, because in order to figure out increasing, decreasing, we need a view of the graph. So, f of x equals x plus 2 squared. What is that? What is it? Zoom 6. Grab your calculator if you need them.
It's parabola.
Parabola, right? Officially, it's a parabola moved to left. Okay. We want to know when it is increasing, and we want to know when it is decreasing. So, start at the left. If you start at the farthest left piece, and you start, so we are moving to the right of the graph, moving to the right. What's the first thing you're doing as you draw from the right? Are you going up and increasing or down and decreasing? You always start on the right. So as I start on the right, this is the farthest right, where am I going to go? Oh.
I'm like, you're pointing this side, but you keep saying right. That's why I'm like,
Because I'm having a moment. I'm confused. This is my right because I am backwards. This is my right. Okay, my apologies. Yes, start from the left. It does make more sense, doesn't it? Okay, are we good? Sorry. That's totally me being backwards facing you guys. I usually do better on that. Okay, starting from the left. What do we first do? Are you guys with them? Okay. How far, how long do we decrease? Okay, until we get to this.
you talk about your x value.
Yes, yep. So we are decreasing until you get to that minimum point. And when we talk about telling the intervals, valid point, we are using x values. Okay, so it's from left to right when you start increasing, decreasing, all of that. So here, we started decreasing at negative infinity. When am I going to stop decreasing? Well, what is this minimum? That vertex is at negative 2, 0, yes. What's the x value? Negative 2. So we're decreasing from negative infinity to negative 2.
That's what it is. Because you're not decreasing when you're at negative 2. You're at 0.
Yeah. I have a bracket in my notes, I'm realizing, but my brain is, oh, that's why I have a bracket. Okay. I have a bracket. So negative 2 is kind of our switch point, yes? But here's the deal. Are you touching negative 2?
Yeah.
You are touching negative 2. So that's why I have a bracket there. As opposed to if we run across an asymptote, we are not touching it, and that's where we're going to use our parentheses. Okay, so look at it as, are we touching negative 2? Yes, so bracket. I follow that idea too, which is why I paused my brain for a moment. Now, what happens after you get past that point? Okay, now, as I move to the right, I'm moving up, yes? And so that is my increasing. When did I start increasing? At -2. How far am I increasing? Infinitely, right? So infinity. -2 again is going to need a bracket. And reason being because we're touching that. That's a point on the graph. Okay. Questions there? Let's try B then. G of x equals x squared over x squared minus 1. I think we get a fancier graph this time, don't we? What did you say? Okay, guys, we've got this graph to look at, right? And I'm just going to draw a sketch here. Something that I can draw along on the board here. Okay. Now, one thing that would be helpful to think of, well, we'll get to there when we get there, I guess. Okay, starting at the left, as you move to the right, what is my graph doing? So I start over here. It looks kind of flat, but realize, what is it starting to do? It is gradually increasing, yes? So our first interval is going to be an increasing interval on this one. When did I start increasing?
-infinity.
Okay, the obvious piece, -infinity. Now, to what x value am I increasing?
Yeah.
-1? Are we guessing -1 or do we know -1?
Yes.
Now, first of all, can you kind of look and see, I mean, is it obvious there's a vertical asymptote? Okay. The question is, where is the vertical asymptote? Well, it kind of looks to be -1. You can use trace for that, but also go back here real quickly. If you factored your denominator, what does your denominator factor into? Denominator factors into x plus 1 and x minus 1. So where are x plus 1, x minus 1 means there are vertical asymptotes at -1 and +1. Okay, so we are increasing up to -1. Are we going to touch -1? No, because it's an asymptote. So we're going to use a parenthesis. Now, okay, as we continue from the left to the right, where does my graph go next? Where is it next? Where am I going to pick it up at? I'm going to pick it up on the left side of the parabola, yes? As I start drawing this left side of the parabola, what am I doing?
Increasing.
I am increasing. Are you guys with them? Now, we are in, where do we start increasing? The vertical asymptote of -1, which an asymptote again is going to be a parenthesis. What are we increasing to?
0.
Why 0? Because this point here, if you look where I hit trace, this point here is 0, 0, yes? So we're increasing to the x value of 0, parenthesis or bracket. This one is a bracket because we are touching it, yes? Okay. What do I do after I hit that 0, 0 point?
Decrease.
Now we are decreasing. Okay? So, when do we start decreasing?
0.
At 0, the place we stopped increasing. 0 with a bracket because it's a point on the graph. Now, we're decreasing, decreasing, decreasing. What are we decreasing to? What x value? The asymptote of 1. Because it's an asymptote, I'm going to use a parenthesis. Now, after we finish with this parabola, where's my graph go as I move left to right? Now I'm up here, or way up high, yes? As I start tracing from way up high, where am I going? My graph is decreasing, yes? Okay, because I'm moving down my graph as I go to the right. Where did I start decreasing? On the other side of that asymptote of 1. It was an asymptote, so I'm using parentheses. How long am I decreasing? Infinitely. We're getting closer and closer to whatever that horizontal asymptote is there, but not touching it. Okay. It's increasing, decreasing. You'll see a little bit of each of these types of questions in homework, okay? So you'll want the calculator. Remember, you can go in the app portal on your iPad and request, it's Calc 84. You can also get that on your phone. I know it's on Android. I think it's on iPhone. I know there's something on iPhone. I think Calc 84 can go on the iPad. Okay, next topic, boundedness, okay? We're going to look at some examples of what it means to be bounded, okay? If a graph is bounded, I think of it meaning it has a boundary it cannot cross, or that it doesn't cross, okay? If it's unbounded, it goes on forever. So, as we look at this, okay, this first example looks a lot like the graph we just looked at, right? This is an example that is unbounded, okay? You would often probably see either not bounded, or you would also see it says unbounded, because what's happening? We're talking vertically here. This graph is going to go infinitely up. So it's not bounded above. It has no upper boundary. It's going to go infinitely down. So it's not bounded below. It has no bottom boundary. So that's an example of a graph that is unbounded or not bounded. Now, this next example. Again, you can see it's going to go infinitely up, yes? Infinitely up means there's no upper boundary. There's no maximum value because it's infinitely up. What about on the bottom side? Does it have a point that nothing else goes below?
No.
Yeah, it's not like a bounded line or anything, but think about it. No part of this graph goes below that point right there, yes? So this graph is what we call bounded below. It has a point on the bottom where nothing else goes lower than it. Does that make sense? Okay, nothing else goes lower than that point, so it's bounded below. There's not a physical boundary, but it's bounded below. Okay, do you see this next one here? It goes infinitely down, so there's nothing that stops it below, but what about up high? Does it have a certain level it never goes above? Yeah. And again, it's not like it's a line, but it's just kind of a certain area. It never goes above those points, yes? So that graph is what I would call bounded above. It never goes above those points. And then this last graph. Now, notice what's different about these. There's actually endpoints, yes? If there's endpoints, is it going infinitely down or infinitely up? No. Is there an upper boundary? On top, it never goes any higher than those marks I just made. On bottom, is there a lower boundary? It never goes any lower than those marks, so what do we know? This is bounded, and when we talk about bounded, bounded means it's bounded both above and below. Okay, so it's bounded, meaning bounded above and below. Okay, identify each of these functions as bounded below, bounded above, bounded or not bounded. What's this mean we have to do? Officially graph them. Now that first one, I'll be honest, I could do without graphing. What is that first one? It's a parabola, yes? And it's a parabola that opens right side up. Well, if I have a parabola that opens right side up, what would you say about that?
Bounded below.
Bounded below? There's a certain point. It goes no lower than, but it does go infinitely up. Okay. Now, I don't think you don't have to put this, but I know in my notes, I have that it's bounded below by the y value, y equals -4, or at y equals -4. You don't have to necessarily list that though. Okay, we okay with that one? Okay, this next one is an interesting graph if I recall it correctly. And you don't have to draw the graphs in homework. To me, it's a thing that helps in the notes, right? If you can see it in your notes and you're trying to figure out what that means, you don't have to necessarily draw that. Okay, we have this graph. I don't know if that's a good way to portray it, but it looks something like this. Okay. Can we agree with Paxton? Bounded. Because what's happening here? It has a low spot here, it has a high spot here, but as it goes off infinitely left and right, what's it following? It's following that x-axis. It's not going to continue to go higher or lower. So this one is bounded. And remember, when we say bounded, that is the way for saying above and below in the same thought. Okay? It's just the short way. You don't have to say bounded above and bounded below. You just say bounded. Okay. Are we good there? We got one other section. We'll see what we can do with it real quick. Okay, first of all, stick in your head the word extrema. Are you familiar with the word extrema? Okay. Extrema, the hills and valleys of our graphs. Or in other words, the maxes and mins. Okay, so whenever you're asked to find extrema, it's a fancy way of saying find the maxes and mins. A local max or min is one of the hills or valleys of our graphs. An absolute max or min is the highest or lowest point that the graph ever goes. So real quick example, so you have something. Like with a parabola here, this is obviously a minimum. Does my graph ever go any lower than that? It does not. So this is an example of an absolute min because it will not go lower than that. Flip the parabola upside down, and this vertex is an example of an absolute max. Absolute means nothing will go higher or lower than that specific point. Now, I just drew a cubic up here. Do you see mins and maxes? Well, right here, where I just put that dot, that's a max. But is that the highest spot the graph will ever go? No, because it goes infinitely up. So this is what we call a local max, because it's a max in that little area. It's a max relative to the graph right there beside it. And if that's a local max, guess what? That's a local min, because it's a minimum in that little area. Is that the lowest the graph ever goes? No. Okay. What was your question?
It wouldn't just be like where the graph cuts off, so like where the arrow is. Because you can see the.
No, because when you're looking at the calculator, the graph doesn't just cut off there. So, okay. Well, the ones you will see, and we can put this one on the calculator real quick. Decide whether the function has any local maxima, local minima. If so, find the values. State whether or not the values are considered absolute. So if you graph this on your calculator, you're going to get something that looks like that. Go ahead and graph it. I know I'm running out of time, but we need to look at this. So you can at least try and play around with it at home, or whenever you're working on homework. Now, shoot, I really am going to have to talk about this more tomorrow. You can see there's going to be a minimum over here, yes? So a zoom out function would be good for that. Remember if you...
on the graph.
Huh?
But it's still on your graph, so it would just be absolute.
Okay, but you still have to find the value. So I'm going to zoom out. Remember, hit enter an extra time. Now, what I like to do here is ZBox. I haven't taught ZBox yet, have I? ZBox, you can draw a box around whatever you want to zoom in on so you can find it. And so if I draw a box around here, shoot, I just hit the whole thing. ZBox is number 1. Draw a box, so hit enter to make your first corner of the box. Use your arrows to go to the diagonal corner. And hit enter again, and it'll zoom in so I can see the graph a little bit better. Okay, but here's what you need to play around with. In your calc menu, second calc, we've used 0. What other options are there? Min and max. So if I pick minimum, these questions look familiar, left bound. So I'm going to go find my left bound. I'm going left of this lowest point. I'm going to hit enter. Give me just a second. Right bound. So now I'm going right of this lowest point. Enter. The guess, you go back to your minimum and you hit enter, and you have your minimum point. You can do the same thing with maximums. Okay? And that now, you have to do them each individually, just like zeros, right? Okay. Here's what I want you to do. I know I'll have to talk about this a little bit more tomorrow, but I do want you to do the homework. Okay? 22 through 46 evens on page 93. Do the homework to the best you can. Give a good effort at everything. Play on the calculator, right? If it doesn't work, it doesn't work. But play on the calculator.
So like that bottom one, we have to zoom out for, would that be considered absolute?
It would be an absolute min, yes. So right here, you're going to have an absolute min. Here you're going to have a local max. And here you're going to have a local min. So we'll talk about that more tomorrow. I'm going to go ahead and let's see. Local max 0.46, 1.32. Local min 1.60 and negative 1.77. She is throwing stuff at me. Absolute min negative 2.06, negative 24.06. And this is in our calc menu. So second calc for trace. And then you go to either min or max.